Alright. Hi everyone, thank you for coming. Today I'll be going through a new topic which I've been focusing on, which is resource management in multifunction radar and networks. I'll go through a brief introduction to what resource management is and how it differs and how the complexity increases when we're considering the network, and the concept which I'm trying to portray in my research, which is information sharing, and I'll show how that differs to information fusion. Then I've got some preliminary results for the proof of concept and how I'm using quality of service to model or formulate the problem. So a multifunction radar, as the name suggests, it has the capability of carrying out multiple functions, and it does this by utilizing a phased array where it can form multiple transmit beams and maneuver these beams at extreme agility. And because it can carry out multiple functions, it can replace a suite of radars. As we can see in the image here, where a multifunction radar is mounted on a naval ship, it can carry out all the functions, as you can see, such as surveillance, tracking multiple targets, target classification, missile launch. The issue, or one of the challenges, is how do we distribute resources such that we can carry out all these tasks in the most optimal manner. And also, as you can see, a multifunction radar possesses the ability to dynamically change its operating parameters. So, for example, if it was spending too much resource, such as dwell time, on tracking targets, in order to be able to carry out surveillance, it can modify its parameters such that it can get a global optimal performance out of all the functions. So the problem of resource management itself breaks down to two separate challenges. The first one is parameter selection, and it's also referred to as resource allocation. And the second challenge is scheduling. At the moment, I'm currently focusing on parameter selection, and eventually I will dwell into scheduling later on in my research. So the challenge in parameter selection is, how do we know what parameter to choose for each given task, such as dwell time, revisit interval, or even the waveform that we're transmitting. And we need to choose this parameter such that we know how much optimal amount of resource we require to allocate to that given task. There are two different types of resource allocation or parameter selection algorithms. The first one's heuristic algorithms. The second ones are optimization algorithms. The heuristic algorithms aim to solve the problem through obtaining an approximation or approximate solution, and they do this by trading off optimality and accuracy. But they do it the computation load is very little, and mainly because they don't require too much math to obtain that approximate solution. The second class of algorithm, what I'm focusing on, is optimization algorithms. They are very mathematical. What they aim to do is obtain a near optimal solution, and they are quite computationally heavy, but with increasing technologies, this doesn't present too much of a problem for us right now. The second part, as I mentioned, is scheduling. So scheduling is basically trying to create a timeline for the radar to execute each task. There are two main types of schedulers, interleaved and non-interleaved. Interleaved scheduler is simply a scheduler which is able to exploit the two-way time delay between transmitting a signal and receiving the echo. So what it does is it illuminates a target for one pulse, and then it stares off and carries on executing other tasks until the first echo from the target comes back, and then it can illuminate again. A non-interleaved scheduler does not have that capability, so it stays at one target or a surveillance patch and finishes the dwell off before it moves on to the second task. So at the moment, Fraunhofer, FKIE are currently leading researchers in this field, and they mainly been using quality of service algorithm, and something which is what I'm focusing on as well. They focus mainly on using monostatic or resource management in monostatic networks, and they've recently started to look at resource management in a network consisting of active nodes only. I could not find any publications or literature for resource management in a network consisting of active and passive nodes. So that's one of the main reasons why I want to look into it, because it looks like it's a very interesting topic, And since the passive nodes do not transmit or have the capability to transmit, they naturally rely on the active sensor, therefore requiring a centralized network. Therefore, in a nutshell, the aim of my research is to demonstrate through simulation the optimization of resources in a centralized multifunction radar network consisting of active and passive nodes. So it's easy to see when we are managing resources within a network, the complexity increases because we have multiple nodes and we need to know how to coordinate all the resources and tasks within this network. And in order to realize the full potential of the network, the resource management decisions need to be based on the aggregated perception of the environment from all the sensors. In order to do this, the first idea or the concept that jumps to mind is information fusion. And this is not something that I'm implementing in mind. I have my own idea or the concept, as you'll see later on. But with fusion, we do have advantages such as increased performance, but these advantages are only realized if and only if the fusion process is carried out in an accurate manner. The disadvantages are increased complexity, requires large communication bandwidth. Computational load is increased as well, since not only are we required to process the signals, but as well as the fusion method. Fusion, we need to think of it as a double-edged sword. So for example, if we obtain corrupt data from one sensor and good data from a second sensor, combining this, we would usually end up with a corrupt set of data, which will have a severe impact on our resource management decision. And it also requires uncertainty theories to facilitate the whole fusion process. And I personally don't think it's very practical for resource management, considering that resource allocation decisions need to be made within 3 seconds, 1 to 3 seconds, and the scheduling decisions need to be made in less than 1 second. So in order to describe the concept of information sharing, we first define fusion, which is the act of binding, combining 2 or more sets of data to form a single entity, which differs from information sharing because in information sharing we select the best set of data obtained from all the sensors and then make the resource management decision based on that. So in information sharing, we aim to delegate the given task to the best suited sensor within the network, which aims to utilize resources within the network efficiently. It has several advantages of fusion. The main one is simplicity, because we do not need uncertainty theories. We avoid the fusing process itself, lower communication load, lower computational load, as well as it tries to balance the load between the sensors. The disadvantage, it does have one, which is, or probably more, the only one I could think of this. The sensors may provide very similar information, and hence the perception of each sensor will give us the same resource management decision. So here's a simulation that tries to show the concept of information sharing. So we have our network layout, as you can see here, with a bistatic node to the left, 50 kilometers from the monostatic node. We have plotted 200 targets, which are stationary point targets, with RCS ranging from 1 to 10 meters squared. And the network, as you can see, consists of only 2 nodes, both with a 120-degree field of view. The resource here, which I've modeled as dwell time, and the aim of this network is to delegate task responsibility to the best suited sensor. And we defined the best suited sensor as the one which maximizes SNR per resource use. In order to portray the concept, we assume infinite resource and full schedulability, which are quite strong assumptions, but later on I will relax them using the quality of service framework. So in practice, usually there's a predefined performance level, such as what are we happy with, what level of detection rate or what level of accuracy. Here I assume a 13 dB SNR, and we allow the Monostatic to adapt its dwell time to achieve that, such that we use the most optimal number of pulses to integrate. What we see on the left side, which shows the SNR, or the distribution of SNR for the targets within the simulation, most of the targets end up in the 13 dB bin, which is what we want. And some of them do have greater than 13 dB SNR. But we have no control over that because the SNR is just higher since the targets are closer in. In the second one, this is what the bistatic bin observes. We can ignore the bar in the 0 dB bin because these are just the targets which do not fall into the overlapping area and these are outside the bistatic field of view. What we do see is that there's a significant amount of targets which have much greater than 13 dB SNR. That means we can reduce the dwell on these targets and achieve a lower SNR, which we're still happy with, but the whole point is that we save resources and spend these resources where they're more required. Another way to view the results is, on the left graph, we see the target number and the absolute difference in SNR between the two nodes. We can see on average there's around 2 to 3 dB difference. There is one odd target out, which has around a 9 dB difference between the two nodes. On the right-hand side, we see some results here, which is the network incorporating information sharing. So, for example, the first line, the blue line here, the straight line, this is a monostatic which does not have the ability to adapt its dwell. And what the graph is showing is the aggregate dwell time required to update position on all the targets. What we can see is that the monostatic which does not have the ability to adapt its dwell takes roughly 7 seconds in aggregated dwell time to update the position on all the 200 targets. The monostatic on its own, with ability to adapt, takes roughly 4.3 seconds, but the network incorporating information sharing takes only 3.2 seconds. So what we can conclude from this is that we can save on average around 25% resources for the specification geometry used. And I think this is strong enough results for us to say, hey, you know what, this is a viable idea to look into with a lot more realistic assumptions. So now I'll start using the quality of service to relax the assumption of infinite resources. As you guys, most of you would know that quality of service is extensively used in telephony and computer networks. It's a method of, it's actually not optimal because it's an NP-hard problem, but it tries to achieve a near optimal solution in terms of distributing the resources to the tasks that need to be carried out. So it's a multi-dimensional NP-hard problem which I'll relate to the radar by first defining all the dimensions and the quality space that we require to formulate the problem. So the first dimension I define is the radar parameter dimension, which is all the parameters that the radar has control over, such as dwell length, revisit interval, and the waveform. The shared parameter dimension is the dimension in which the tasks overlap in the area for both nodes. And then we have the environmental dimension. These are the parameters that we do not have control over, such as target RCS, range, bearing, and the maneuvering of the target. And then we also have the resource space, the quality space, which is the tracking and surveillance quality. And then what we do is map the task quality to task utility to create a utility space, which allows us to obtain a normalized performance measure to allow comparison between all the tasks. So I've taken all the boring maths out, just giving you how I formulated the problem here. So we start with an M-node network, which is required to execute the given task, where the total number of tasks is defined by K. The radar parameter dimension, for example, for task 1 is defined by P, where I here shows the radar that we're considering all the parameters for, and that 1 represents the task number. Therefore, by capital P, we can say all the radar parameters for all tasks and all nodes is given by the following vector. Thus, task quality is defined as the parameter selected together with the environmental dimension. The task utility is mapping from task quality to task utility, which again converts it into a normalized performance measure. And our aim is to maximize the global utility defined by U, subject to the resource constraint that the resource that we consume, or the radar consumes, has to be less than the total amount of resource available. I am missing an inequality sign here. This should be less than or equal to 0. So I carried out a simulation to see the tracking performance of the network versus the monostatic node. So the way I define my resource here is dwell length over the revisit interval. So we can see logically, if we increase our dwell length, which is favorable, we increase the amount of resource consumption. And revisit interval, if we shorten our revisit interval, we get a better tracking accuracy, and hence our resource increases. So what I've used is the Vancouver model, which simply shows, or simply tries to keep the angular accuracy or angular uncertainty below a certain fraction of your beam width. What we see here is that as we go forward in time, the angular uncertainty increases until we take a measurement of that target or the tracking measurement, and then the uncertainty drops, which is known as the variance reduction ratio, and is defined by the variable u. And the capital T here shows the revisit interval required to obtain that angular accuracy. And then I've defined my task utility function, as you can see here, where VE is our track sharpness or estimated track sharpness. In literature, it's been defined that if the track sharpness exceeds 0.3 of your beam width, then most likely in practice you will lose track of that target. So in our utility function, we incorporate that as 0 utility if we are greater than 0.3 of our beam width in terms of track sharpness. So here you can see the intricate workings of QRAM itself. So what we do here, or what this graph is showing, is the amount of resource used per utility, for example, tracking tasks. So we'll have these type of utility curves for all the tasks available, so it can be 50, 100, 200. This one is defined using dwell length and revisit interval. The aim here is to first extract the concave majorant, which is the most efficient curve, which is right at the top, and that can be defined as the one that gives you the best utility per resource used. The aim of QRAM here is to find the optimal operating points for all the tasks, given the resource constraint. Here's another example of the concave majorants have been extracted for a given task, for both bistatic and monostatic node. What we can see here is that for a 0.7 utility, the bistatic requires less resource relative to the monostatic node. And in this scenario, the way that I will construct the algorithm, in real time, what in this case it will do is reject the monostatic curve and say that bistatic is more suited to take responsibility on for that tracking task. Here's another simulation which actually tries to compare the benefit of the monostatic node versus the network. We have a different number of sets of target with, and I've assumed that 100% of the resources allocated to tracking, and the velocity of the targets range from 50 to 300 meters per second. What we see here on the left-hand side, which shows the number of targets being tracked against the resource used, we can see that the network always consumes less resource, and if we compare it to the graph on the right-hand side, we see that the network always has a better tracking sharpness, which so the graph showing the number of targets versus track sharpness. Roughly, what I saw was around for 50% less consumption, the network will always have 15% better track sharpness. But in one of the simulations, I did see that as the number of targets increase, the amount of benefit produced by the network is very marginal, around 5%. And I think that's to do with the transmitter being saturated, because there's only one transmitter that we've deployed, and it's only so much one transmitter can illuminate and achieve a reliable track accuracy. In the previous example, I had 100% of the resource allocated to tracking, and in this one, what I've done is, what I'm trying to show is how the performance of the network versus monostatic changes when you have a different degree or different amounts of resource allocated just for tracking. So right at the bottom we have 10%, so we range from 10% to 100%, and this is pretty much just 60 targets, RCF ranging from 1 to 10 meters per square, and the velocity 50 to 300 meters per second. And what we see here, the network shows anywhere from 8 to 30% increase in track sharpness for the same amount of resource being used. So in conclusion, what I can see is that currently I can see that the radar or the network incorporating information sharing shows significant advantages over a single multifunctional radar. The network does provide a better track sharpness at lower resource consumption, but this is limited to, well, it does change depending on how many targets are in the environment. As I mentioned, for large amounts of targets, the benefit is quite marginal. However, I don't think I've analyzed the full performance of the network currently because I have assumed perfect scheduling, and this is something that I'm currently working on now. And I think once the scheduler is built, even when there's a dense target environment, I think the network will show a lot more improvement than a single monostatic radar, because then we'll be able to spread the scheduling load amongst the two sensors within the network. So my future work, or in the near future, I'm trying to first focus on creating a scheduler to coordinate the task execution between the sensors in the network, and see if there are other performance measures to analyze the two, or to analyze the network and the monostatic. And then I want to look into multiple transmit beams and how that may affect the resource management decisions, and then expand to multistatic case, and hopefully I should be able to see the effect of pulse chasing on resource management as well, and finally communication link modeling. Thank you.